I mean, this is brutal, and on top of that, I'm going to set a self-limiting timer. So if you fail to interrupt me, I will interrupt myself. But and on top of that, I guess I don't need this mic. Um, I'm double mic'd, like I need to. Collective consciousness is not really consciousness. In the social sciences, collective consciousness refers to the kind of co-awareness that you have a shared set of interests, right? And so I'm really going to be focusing on the subjectivity and the degree to which those subjectivities become sufficiently shared that they emerge into a variety of kinds of collective action. So from simulated subjectivity to collective consciousness and large language models. So I'm a sociologist. One of these things is not like the other. And I study how it is that knowledge emerges and combines in collective systems where we share data, via sensation. We share, descriptions, explanations, predictions, and plans, and the context of creating collective action. So I think about how it is that collectives as systems think and how those collectives can think better relative to specific values. And my broad kind of interest is, okay, can we observe innovation at one level such that we can build sufficient models to simulate and automate innovation? So I take kind of Richard Feynman's claim that, if you don't grow it, then you didn't explain it, right? If you didn't create it, you didn't understand it. And so I spend a fair bit of time working with driving AI in the context of material sciences, pharmacological work, and investments with government and other innovation investors. And I would say, so the social observation that I see over and over again, I'll start with kind of a handful of observations, and then we'll think about how LLMs are able to model them, and then their limitations now, how we can kind of hack and correct for them to improve these, is this idea of the wisdom of crowds that Francis Galton kind of proposes in Vox Populi, this 1907 Nature article in which he kind of shows that in this West of England fat, stock, and poultry exhibition, that basically of the 800 or 787 were the number of tickets that were collected and counted, that the average, the mean was less than 0.1% off. It was about a pound off of the total average, and the median was 0.8% off. Now, one of the things that he didn't characterize was the diversity of data and approaches that were underlying basically those individual guesses of the weight of this ox, right? Presumably each of them had their own oxes, right? They knew their weight, their relative weight relative to this provided a different set of perspectives. And so I'm really going to be focusing on how, in the context of science, technology, business, and society, how there's this wisdom of diverse and disconnected crowds. And by diverse, I mean cognitively, perceptually, experientially, and identity. And there's a kind of a stupidity or myopathy of similar or connected crowds across these contexts. And so my interest really is then in building AIs that are not monocultured and cropped, that actually facilitate the diversity that might allow us to engage in sustained and continued innovation. So a few observations. One of the things that we see is as fields grow across time and space, there's this exponential decline in the likelihood that new ideas get cited in the canon, right? In the most popular things over time. If we build a model, this is a very simple hypergraph embedding model. So imagine we've got this surface and we've got keywords in the surface, and we're trying to pull down a hypergraph where each edge, right, hyperedge, is basically the paper, a paper in the next period. So we're trying to predict all the papers. We build this manifold by just wrinkling it so it maximizes the likelihood of pulling down the papers that occur in this year. And then we allow this to move with Brownian motion over time. And then we pull down our hypergraph for next year's papers and see the degree to which it predicts those papers. And the good thing is it predicts most of the papers, which is to say we've got AUCs of about 0.95. So why is that? It should be obvious. We're inertial, right? The papers that we wrote last year are pretty similar to the papers we wrote this year. We're bumping around in concept space. But the problem is that if we look at the papers that show up that are the least likely under this most likely model, the least probable under this most probable model, they are the best papers, right? So by far the best papers. In fact, improbability under this model itself is the best ex ante predictor of attention in the context of science. So for example, I can predict about almost 60% of the likelihood of being in the top 10% of citations in the next period, just as a function of basically rewiring or distorting this space, which has constructed this most likely model. And who creates those most unlikely papers that attract this disproportionate attention? 70% of them are from surprising people. So people who have careers that combine surprising combinations of elements in the space, surprising teams. This is lower levels of novelty. And at the higher levels, surprising expeditions where people from one part of this kind of collective cognitive space travel to another part of the space that's never seen anyone like them before. Their space has never seen anyone like the place they're traveling to before. And they propose something with alien or outsider methods that is surprisingly or improbably successful in the context of that engagement. And how do we generate those things systematically? We generate those by accident. So if you look basically across all of people, so this is a survey of about 100,000 academics. We select people across the citation distribution. We select randomly papers inside their thing. We ask them how influential those papers were in the intellectual contribution of this paper. And we find the biggest signal is people who are in the same institution but not in the same department, right? So they're people that, like, you show up at the Whole Foods together. Your kids are on the same soccer or football team together. You know, you're like serving in the same, dumb committee together. Like you're forced together. And these are also these are the furthest from you in semantic space if we embed them according to any reasonable semantic embedding. Moreover, if we think about the distribution of teams across this space, we find that we do much better from having many more independent smaller teams than larger teams, both team for team, but also across the distribution of teams. So if we are thinking about, for example, the disruption of a paper, which in this case is just measured as the structural likelihood that you eclipse the work on which you build. So people cite you as like T1, they forget everything that you've built on before. We see as team size grows up, and any way you slice this distribution at any team size, there's an exponential decline in the likelihood that you will disrupt that frontier, right? And part of this is because basically big teams are doing what big production companies do. They're betting on yesterday's successes. So it's like, if they're going to pick like the next paper, or the next movie, it's going to be Transformers 9, rather than, Slumdog Millionaire, and so that's what systematically is happening is they're hedging their bets effectively, kind of like betting on the crowd of yesterday, which means they're much less likely to be influential in the future. The same is true when we look at team structures. So if you take, all of the papers in the canon and you take the position that people take in those papers, right? So are they leading, writing, supervising, coordinating, designing, interpreting, or conceiving? Are they analyzing, developing, collecting, caring, or performing? Or are they editing, commenting, discussing, contributing? So I'm just going to loosely call these brain, muscles, and fat. I mean, that's, of course, a crass distinction. But if I look at the ratio, basically, of brains to the rest of the pieces in this space, I'll call that a leadership ratio, then the more people, the more brains that are activated in the context of any particular team, you have much more likely to have novel outcomes, which is to say novel combinations of elements within the team. You're much less likely to only favor the productivity of the top leader in the space, and you're much more likely to be predictive of things that will be important in decades to come, right? So it's kind of like, big team papers that are betting on the immediate past are predictive of the immediate future. All their citations happen tomorrow, effectively. Like, I would say the biggest example of this would be like the Genome Project in 2000. Like almost all of the citations happen within a year and a half of that paper. We can find the same thing in terms of diversity, not only for discovery, but also just for validation. So if we think about something like the replication crisis across fields, we find systematically that centralized communities generalize or generate much less replicable results. So in this case, we basically go in, we find hundreds of thousands of claims in the literature, we line them up with high throughput of experiments, where we're performing the same experiment 200 to 500 times, like through robots, but these are wet lab experiments. And then we ask, to what degree does the structure of the team, right, end up influencing the likelihood that those findings replicate in the future? And we find systematically that when there's basically high social independence, or when there's low social independence, which is to say lots of overlap between the people, lots of overlap between the methods, lots of overlap between the prior knowledge, then you systematically have this kind of collapse in the likelihood that those findings will replicate in the future, because it's not, 100 replications, it's like 1.5 replications, per the 100 papers that were all produced by the same network of people across this space. And we can find that we can predict the likelihood that ideas and subfields will collapse as a function of their inability to diffuse beyond the initial authors. Right, so the same thing that we see like pump and dump stocks schemes on the internet, we see in the context of the scientific landscape. And we can use this to perform a Bayesian update on the literature, to discount things that are echoed interminably between the same teams with the same methods and the same underlying assumptions. We can undertake competition policies in granting agencies, either by simulation or by experiment, which we're doing. But the question then is, all these things were observational. Like, I'm just looking out in the world at 30,000 feet at how it is that scientists interact. I could spend a lot of time talking about that, but I'm dubious about those results insofar as how much of those are selection. Like, how much of those are just the result of, like, we're only picking the best things. We don't really know what the distribution of other things are. What can provide policies in and out of context that could be useful? So this requires us to build sufficiency, models that are sufficient to kind of construct these kinds of outcomes so that we can drive, for example, more effective and efficient world funding. So one approach, this is like so washed out, you can't see the underlying thing, is automation. I'm not really going to talk about that today, but I will just say I spend a lot of time automating experiments, building AIs that kind of like draw in experimental subjects, that theorize about those subjects, that are phenomenologists to select the next experiments, either using the classic kind of like explore, exploit, or doing what we just saw happens actually in science, where typically the surprising things are the investigators that generate the most likely advances are actually just using a completely different map. It's like they're finding the Eiffel Tower with a map of London. I mean, they're directed in alien ways to these initial spaces. So one is to automate these experiments, and we spend a lot of time engaged in automation. The second is to simulate them, and so to build digital doubles, which in this case, what's a digital double or a digital twin? Lots of people are talking about them. From my definition, I'm going to call these data-driven generative models that allow otherwise expensive or impossible observation, interrogation, and simulation when you lack sufficient, by sufficient I mean almost completely characterizing models, first principles models, right? So, and I would say this covers almost every area in social and behavioral science. And we're not unique, right? So in chemistry, yes, we've got really strong predictive models for, single atom interactions. We have terrible models for polymers, right? So long, gangly, social network-like molecules. So this is an advance and opportunity, I would say, for a number of different contexts. So I'm specifically going to just build today, there's lots of other models we build. Today, I'm going to talk about large language models of human subjectivity and collectivities. As you all know, so I'm not going to linger on this. Large language models are the love child of autoregressive language modeling, so next word prediction language modeling and self-attention embeddings. This is the self-attention stack precisely that's 96 times replicated inside the belly of GPT-3, which was the last of the OpenAI published models. And basically the whole setup is just trying to ask this question: for word Q in the sequence, what are the most informative words K, right? So it's basically just asking this question over and over again through this setup, and then stacking them to predict the ultimate next word. So I'll also take as kind of my inference or interpretation of inference, this kind of transformers learning context by gradient descent, or these kind of meta learners, which suggests that the relationship between the number of self-attention layers is correlated, highly correlated with the number of steps in gradient descent. So we're basically optimizing this response over some pre-trained cultural world model in context learning. And why is it continuous? Well, the math is a lot easier in continuous spaces than it is if we were to think of these as networked words, not necessarily that there aren't discretenesses to the concepts. So now what do we do with these models? Well, one thing we can do is we can, simulate survey subjects. So this is the general social survey. We just, we basically we fine-tune a semantic model. We basically build an individual belief embedding, started with randomization. We build a period embedding, and then we, through cross layers, produce this a specific agent for each agent inside the sample as a function of the other things that they've been asked and answered, either in the past or in the present. And so we can basically do a strong job on imputation and retrodiction. Even with zero-shot prediction in a simple model like this, we do much, much better than random. So these are questions that will occur in the future that haven't existed at the time of the sample. Here's a more straightforward example. So in a GPT-3 model in this case, because they have internal embeddings, we can just tell it, through in-context learning, I'm a conservative and Republican, I voted for Donald Trump, I'm a liberal and Democrat. Now, this model was trained in October of 2019 before COVID became something that entered the world stage as an identity. And so now we're going to teach it about COVID. I mean, this is all we teach it, like literally. Lately, one of the big political issues has been COVID-19. And students should be required to receive the COVID-19 vaccine, or businesses should be closed until rates of infection go down, or whatever. And then we just ask the model to say what it thinks. We allow the model to code what it thinks. We just take the difference between the vector for good idea and bad idea. We project everything at right angles to that space. And then we predict the likelihood that Republicans or Democrats in 2019, as a function of their political proclivity, would have favored or not favored particular policies in March of 2020 after COVID kind of runs rampant. And our predictions are about 90% accurate. So basically, Republicans only preferred border closings, surprise, surprise, and the elimination of any mandate inside the space. But this, basically we're finding, we're trying to identify the degree to which kind of cultural position in the past through this dense space of correlations facilitates the prediction of cultural responsiveness in the future. And where things deviated, we can go back and find that cultural events, unlikely events occurred. Trump, for example, took an unlikely position, which changes basically the unfolding landscape and consequently our prediction about how it is that people of different dispositions will respond. It turns out you can do much better if you don't just look at the top layers of the model, if you can go into the model itself, right? Consider the fact that large language models are predicting the next word, right? If we're trying to basically have them predict the next task or basically a larger subjective position, we do much better by diving deep down. This is the stack of, in let's say GPT-3, 96 layers, and GPT-4 it would be, more than 1,000 layers in the context of Llama. Here it's somewhere between 15 to 25 layers. You end up getting much better prediction of arbitrary tasks like apple, arrow red, lime, arrow green, plum, arrow purple, right? And I'm a Republican and my perspective is, boom, if I grab this theta, right, deep down inside the stack, I do much better predicting the out of sample positions of people or perspectives from that position than I do if I take the vector of that person at the top level inside the space. So here I'm just subtracting the vector for the position of a Republican and Democrat, and I'm scoring it against each word of an essay on abortion, right? And it turns out that it does really beautifully, not just here, but beautifully in even kind of out of sample, like what would a politician who hasn't revealed his or her position on a particular issue, when it's revealed, do we get that right? right? So do we get those positions right? And we do much better through these simulated personas as tax vectors. So think of then here, people are just vectors in the space. I'm going to violate that assumption in a few minutes. That's one way to think of them. And we can use those person vectors. So for example, if I'm a person who's a creative, who's produced articles or patents or screenplays or Wikipedia articles or video games, we've measured all of those in this context. If I basically position my vector as a function of my prior creative output, the likelihood that I combine two ideas is proportional in these high-dimensional large language model spaces of the angle of myself relative to those ideas. So as I move further away, the angle gets smaller. If I move to one side so that one idea is occluded by the other, effectively the answer disappears. This predicts word adoption, word abandonment, word combination, and the likelihood that the whole system innovates at basically the kind of plate tectonic collisions in this broader cultural space that we trace out with these large language models. We can also predict how it is that individuals will respond in naturalistic contexts. So here, we're trying to predict what inferences, and these inferences are discoveries, what discoveries in material science and pharmacology will be inferred cognitively by everyone in the system and by particular people inside the system, right? So here, we just take each paper, each paper has materials properties, and they have people, right? So now I'm going to run a random walk through this space 1 billion times. So I'm going to jump from, let's say photocatalysis to a paper with photocatalysis to a person who wrote the paper to another paper by the person to a material on that paper to another paper with the material, 100 times, 1 billion times. I'm going to embed that in a language model space. So that's proportional. It's a simulation of the likelihood that someone will infer that this property is had by this material as a function of experience and conversation, right? That I've worked on this and that, or I've conversed with someone and I have this experience and they've had that experience. And so we're basically embedding this mixed directed hypergraph. And when we basically predict the likelihood that particular materials will be discovered just by adding this kind of authorship, the set of authorship vectors, we end up improving the prediction of what gets discovered from 50 to 500% in the space across 100 drugs, 450 diseases, about 10 energy-related properties. So these are all materials that are discovered across all the literature to have these properties. And the reason why they work, so our AUCs of prediction are from 0.88 to 0.96 is because we're just, these green densities are the density of people that are there to infer that this thing has that property. So we're just predicting these ridges in the space. The black dots just suggest they're the right predictions. And we're predicting with a precision of about 0.45 exactly who makes that discovery. So if you say, oh, this particular copper compound is discovered to have photovoltaic capacity, I can say with 1 and 2 who is going to, of the space of people who are working in that space up to that year, who in 1 of 2 is going to make that prediction, because it's a super high dimensional space. And there are very few people in that high dimensionality who are between this material and this potential inference inside that space. Now, we can not only build digital twins with this, but we can also avoid. So you can imagine, well, why are people all in those places? Well, they're because we have a physics department, a chemistry department. We have like very 19th century divisions between fields across the space. Can we build cultural aliens or cognitive aliens that avoid the human path? And, to what degree do they perform in the space? We find that we build, I'll call these cultural aliens. So we're building predictions that are they're just going in these valleys. So these are things that they have scientific plausibility. For example, the protein-protein network suggests that they might be plausible, but there is nobody there to infer them. So if we make those predictions, right, then we end up doing better if they're discovered years or decades into the future. Surprise, surprise. But they do better in variance and on average. So these are better predictions that suggest that there's basically diminishing margin returns to theory. Like we've squeezed the last drop, and we're going to squeeze another one rather than basically looking for other trees in the forest. Now, we can take the next step, which is like, okay, how can we move from individual subjectivities to simulated interactions that are productive, right? And in this case, we're looking at misinformation detection online. We've done prior work that shows that if people tag other people's misinformation, it's kind of like a slap, boom. It actually, rather than reducing the information bubble, it creates an information bubble. People were becoming more diverse before they got slapped, and they retreat into an information bubble as a function of the slap causally. That doesn't happen when we see things like, kind of collective community opinions style things. So, for example, on Twitter, there's someone can tag a source, it doesn't get revealed. Others vote to see how helpful it is. As a function of their diversity, it gets revealed to the poster, and it doesn't have that impact. It doesn't cause them to kind of retreat. There are fewer obscenities in the ones that are voted, unsurprisingly, to have those predictive capacities. So one of the things that we've done is built basically just simulated crowds that cruise around this space and identify. It takes about 6 days to get one of these, and it does effectively slow down the misinformation. Can we produce them, instantaneously, effectively, with zero latency? We can with these models. It's interesting. Most of the effect comes as a function of the subjectivity of the agents that are selecting and conversing in the space. So here's a conversation between Democrats and Republicans. If I just tell the model to be a Democrat or a Republican, I get 70% of the benefit of creating a conversation, just because that vector is close to the effectively a hyperplane that separates kind of truth and falsity in this misinformation space. We do the same in both measuring and simulating advances in the context of creatives who are producing screenplays, new company descriptions, or new entrepreneurial ventures, new articles, new patents, where we identify a kind of an optimal diversity that lies between people who have maximally different angles with respect to the creative product, but they're close enough to each other that they can understand one another in the context of these spaces. And then finally, this is the kind of the sleight of hand collective consciousness. When we do kind of, I'll call this a kind of a ridiculous experiment. This is coming out in ICML this summer with Dawn Song and her postdoc and some folks in my lab, where we just build a cocktail party of LLMs, right? We just invite them to like find another LLM they'd like to chat with. They chat with them for a while. We have them pick another one. They pick another one. They have a chat. We don't tell them what to chat about. We don't tell them, where to go. But we find over time that they start converging to a set of clusters that repeatedly find others that are either like the ones that they've conversed with, or ones that are like the ones that they've conversed with. And by the end, they're not even speaking English. They're like Chinglish, like English, Cyrillic, Chinese characters. I mean, each one has its own bizarre dialect or idiolect. And what's interesting about these kind of emergent self or cross-trained communities is two things. One, they generate enough diversity that they're much more successful at kind of solving creativity tasks if you grab them out of the box, even than if you design, like hand design perspectives. They've created their own kind of self-entrained perspectives, and they're more immune from basically selfish or poisoned agents that are dropped into the space. If we have a cascading set of like public goods games or other kind of collaborative game theoretic experiments, we find that basically those that were cross-trained within these communities are much less likely, if they're shafted by a selfish agent, to pass along that shafting to people inside their community, because they recognize the difference between the agent that was shafting them and the culture and the language of the agents, as it were, that they were typically picking to converse with over time. So we're doing a bunch of other simulations of conferences, predicting conflicts, collaborations, dating outcomes from tweets and chats online, etc. And then the final piece of the talk, I wanted to basically suggest, okay, you can use these things to simulate social activity, to predict outcomes, to generate outcomes that are different from those outcomes, that are productive for particular reasons. But for many other reasons, these models suck as basically subjectivities and cultural agents, and I'll describe why in just a moment. So I'm going to kind of argue that these transformers in some ways need social, cultural, behavioral science more than sociocultural science needs these transformers. And so I'm just going to walk through a handful of biases and ways in which these are both kind of open questions, but I'll also kind of propose ways in which we might think about and that we have kind of explored hacking or redesigning them to basically produce meaningful and useful subjectivities. And then, I'll kind of close for questions. So one is the fact that there is this kind of like extreme set of biases that are just natively kind of within these models. So there's positivity bias. Obviously, these are friendly agents. They've been designed that way to keep the companies in business. They're also politically biased. It turns out that so in 24 out of the 25 LLMs that we studied are strongly, for example, kind of Biden versus Trump. Now, this was before the debate last night. So I don't know, how but they, and it turns out about 70 to 90% of the bias comes from the RLHF training, right? It's not present for all the open models we have. It's not present in the open models. And it turns out it looks like it could be because of the correlation between toxicity. So this is an essay on toxicity, and this is our underlying Republican minus Democrat model here. So this is, so this is democratic speech, here's how we do toxicity. And when we ask the model, hey, is that biased? The model is like, oh no, I'm actually not, and this, you can't see it, but this is also blue. Like the language of no bias itself ends up being correlated with political position and with many other positions in ways that creates kind of complex outcomes. So for example, these were, I'm not going to share slides, these were highly likely in conversation where they were not asked to change people's opinions, likely to change people's opinions about their decision to vote for one candidate over another. Now one thing that we can do to kind of begin playing with solving these is basically going through a series of simulating experiments where initially we run the simulated experiment and then selectively and adaptively we go out to the real world, to real banks of individuals where we're basically engaged in automated kind of LLM interviews with people from different positions that are underrepresented in the training sample. And then we retune the model and then rerun the kind of the cultural or the social world or the moral world. And then we, again, selectively go out in a kind of evolving experiment. Another problem is these have a massive uniformity bias. So, they're much less entropic than individuals over time. After 3 pages, I can tell with a 90% certainty that it's an LM, just because it's not crossing the fact that, you were writing, but you took lunch, you had an experience, things happened, right? And the same is true for if I were to situate a bunch of selective or simulated agents, it moves to the centroid of the global space. And so it makes them much less diverse than those agents would be individually. So we're playing with basically thinking of individuals no longer as vectors in the space, but of entanglements of vectors in the space, right? And that ends up being much more predictive of not their perspective, not just their perspective, but the likelihood that they combine things as a function of the different perspectives that they embody. We're also engaged in basically building these stream of life models, like basically from cell phone data in urban settings, from Danish registry data in life settings, and we're basically running these models outside. You can think of this as kind of like an implicit model of life. And then when uncertain events occur, we unleash the kind of the reflective, explicit reasoner that improves basically the stream of life models. But the context that these models are continuously feeding the LLMs ends up improving their diversity in ways that are almost completely proportional to the populations that we're sampling. Another problem with these LLMs is they have a massive atemporality bias. So they need to be trained on web scale data. The web is not effectively dated. And so that means that the future is not surprising in the way in which it should be surprising to agents in the world. So I just 2 days ago got a $20 million grant to build chronological LLMs for the purpose of science and tech prediction to kind of facilitate this capacity where we can do effectively kind of cultural causality, right? So to what degree do unusual events in the world change the way in which people think about these things in discourse and the converse, and how can we do that at scale to kind of think about science and technology prediction. So again, recall our predictive models were great for almost everything except anything that was important, right? So the best thing these models can do is not predict out of sample black swan events, but they can be surprised in precisely the right way with respect to those events. The moment those events happen, they can build basically a model of geometric distortion that says, how should you be reseeding and funding and convening this science and technology space? These models have a monolingual bias, so they tend to think in English, not the models that are intensively trained in Chinese, but they tend to think in English and then switch at the last second to the language in which you're asking the question in. And we've done a bunch of other work that shows how different languages think relative to each other. They have very different clustered associations of meanings, and even the information theoretic kind of density of those languages, which shapes things like conversation speed and topic fixity, are dramatically different by these codes. And so now we're working not just to retrain them with different languages, but also to retrain them with these higher order cultural associations embedded inside the languages. Obviously, they have a senseless bias for the most part, and so we're basically working with kind of chain of associations, multimodal ablations, where we have, for example, text to image chains versus text to text change, and we can basically identify the biases that are manifest in the context of vision that are not present in the context of spoken language. We can also, if we want to do inference at scale, because like simulating a society with like millions or billions of people is expensive, we can basically change. Remember, the person was first a vector, then there were a cloud of vectors. We can now reimagine them as the entire tuned vector space. And now 2 vector spaces that include, in my case, all of my similar and different associations, and your similar and different associations suggest everything on which we might disagree and agree, which facilitates a distribution of the likelihood of outcomes from conversation between those agents at much more efficient scales. And then finally, I think we can, these models, do they look like neural networks? I mean, you're brain people, I'm not a brain person, but I know at Cosine last year, there was angst, there was anxiety about the fact of how little brainy or unbrainy these models were. And so I'm a social scientist, and I'm bringing hypothesis like, there's this work in the 1950s about how it is that frustrated triangles and cycles are associated with basically policy instability. This is the second to last slide, I promise. And so we basically say, hey, what if what the ResNet architecture in these spaces is doing is actually quasi-maximizing the number of frustrated cycles and triangles in the space of gradients? And it turns out that it is, and you can tune it to make it more optimal, which is to say more sparse, more efficient. And then what it effectively does is it makes the whole network, it puts it in this critical state, which much less likely to require it's much less likely to require unlearning as a function of path dependence inside these spaces. So anyway, the final conclusion is just the transformers, for them to simulate society and interactions between people, AI, and both, we're going to need more life and social behavioral activity and diversity inside these models to build them so that they can basically facilitate sustainable interaction and innovation. And the conclusion is just really that we want to build ensembles ultimately of diverse intelligences, not only for these advances, but also for the regulation of each other, right? For the regulation of other AIs inside the space, And so lots of people helped out. And my closing questions are really just the ones I already posed. I mean, I posed answers to them. I'm sure there are better answers. And the questions of how do we regulate AI in the world? How do we think about kind of social interactions that are emergent from these different neural networks, and the kind of the unfolding cascade of risks the existential risks even that we might think about kind of being unleashed as a function of these agents. So that's all. Thanks.
Thank you so much. I think for the purpose of time, we're going to take questions over coffee. I also know you need to run to the airport, okay? Because otherwise Santosh is not going to have enough time for his talk. So we will be back at 4:30 with Santosh.